as council member in Indian Mathematical Society, I would like to request sir to address the gathering, to have keynote address. Welcome, sir. Am I audible, sir?
Hello.
Yes, sir.
Hello.
Yes, sir.
I can hear you now. Yes.
Okay,
I
sir.
did not hear you anything before that. Yeah, I can hear you now.
Okay, sir. Sir, it is time for your keynote address.
Yes.
Yes, sir. Welcome, sir.
Thank you. You want to start?
Yes, sir. Yes, sir.
Okay. Can you see my screen?
Yes, sir. It is visible.
Okay. Thank you, Professor Parikh, for the invite. Thank you, organizers and the Ganpati University. It's almost 2:45 a.m. here in the United States. And first time in my career of 28 years, I am trying to deliver a talk in early morning. Let's try. So today I'm going to talk about the solvability of a stochastic magnetohydrodynamic equation. And first of all, I just would like to give the introduction of the problem and which type of terminologies I'm going to use over here. What are the applications of all these terminologies? What is the usefulness? Because the theme of this conference, that is a pure and applied mathematics. My field is control theory, and I like this field because this field, there's a bridge between the pure and applied mathematics. We are using the tools of pure mathematics and applied, try to give the applications in the field of control theory. And as you know, that control theory has lots of applications in all the fields, in economics, business, engineering, real life problems, every field. So let me just start with this one. So first of all, we will discuss about the introduction of the magnetohydrodynamic system with a Poisson jump, and then after we'll discuss about the preliminaries to go for the existence of the mild solution as well as the optimal controllability. After that, again, we will go for the model description and the Rosenblatt process of the stochastic magnetohydrodynamic system, just to prove the existence of the mild solution in terms of the trajectory controllability, and finally the conclusion, the future work. So the infinite dimension system are widely used to represent many phenomena in the real world problems such as the fluid dynamics, heat conduction, reaction diffusion process, etc. And the study of the parameters like the concentration, temperature, velocity, displacement are commonly assigned as a state variable. And in particular, the dynamical system has a Planck equation, the partial differential equation, functional differential equation, stochastic differential equation, and an abstract evolution equation. So for this kind of problem, we require the literature study based on the differential equation in the infinite dimensional space. So first of all, if you are working in the finite dimensional space at that time, usually we provide the solution in the form of using the transition matrix. But in the infinite dimensional space, we have the mild solution. To get the definition of mild, I mean, it's a weak solution, strong solution, all these definitions, I would like to recommend the book of Pazzi. Very nice book based on the mild solution and weak solution in the infinite dimensional space, mainly chapter number 4. And the uniqueness of the problem and existence of mild solution with uniqueness and stability, I mean to say the kind of the well-posedness. And then the controllability problem. There are different notions of controllability, control theory, like approximate controllability, exact controllability, trajectory, optimal, all the different notions of controllability. Let me just give you a brief idea about the control theory. In layman's sense, I would say that right now it's not a good time for so many countries like Israel and Palestine Russia, Ukraine, they are involved in such kind of wars. So let's talk about these things. Suppose we have warplane in the air and you want to hit the warplane with the help of the missile. That means you have to give proper control to the missile so that it can hit the warplane in a proper time period. And if you fix one point on the plane, suppose one point exactly on the wings of the plane, as per example, and suppose you can hit that exactly the point you have decided with the help of the missile, that is called the exact controllability. But both are the moving objects. So to achieve the exact controllability, that is extremely difficult. I proved the first result based on the exact controllability in the infinite dimensional space in my PhD thesis. But again, practically, it is very hard to achieve the exact controllability. But suppose you are achieving engineering, they are always looking for the result. So what happens that if missile hits the warplane, not exactly the point you have chosen, but in a neighboring point, this type of controllability that is called the approximate controllability. Optimal controllability, we just try to minimize the cost functional, and the trajectory controllability. Trajectory, that means we will discuss about this thing in detail, but in just layman sense, I would say that trajectory controllability, that means if you give the control to the object like missile to hit the warplane, that means you give the control and then after in the path along which the system moves, that was not known previously. So I was interested in learning the path because there are two benefits. The first benefit is we can minimize the cost involved in the system, and the second one is we can safeguard the system. These two important concepts actually motivated me to learn the new concept of control theory, and that is the trajectory controllability. So my supervisor, Professor George Nandakumar, and I, we developed this concept in the infinite dimensional space. And then after I generated, that was just theoretical work. I generated the same thing in the second order system, and then after I proved the numerical estimation, numerical simulation, and whatever work we did theoretically, exactly that is matches with the numerical estimation. So that work I did in around 2014, 2015. So that's all the different kind of controllability results. We are mainly concerned over here about the magnetohydrodynamic system. So let me first let you know what we mean by actually this magnetohydrodynamic system and the stochastic form. So magnetohydrodynamic system deals with the study of the motion of the electrically conducting fluids in the presence of the magnetic field. The analysis of dynamical behavior and the magnetic properties of the electrical conducting fluids are nothing but the plasma. And this plasma velocity and density, magnetic field, thermodynamics, pressure, and all kind of self-consistent set, they create the magnetohydrodynamic equation, so you can say system. In the form of stochastic magnetohydrodynamic system is a coupled system compressing the Navier Stock equation, Maxwell equation with noise term. Navier Stock equation is a big thing. Maxwell equation is a big thing. And I'm just combining all these things, Navier Stock equation, Maxwell equation with the noise term. So that's what I mean by the stochastic magnetohydrodynamic system. What people have done. So let me just give you a brief idea about the latest development in the field of the magnetohydrodynamics. The guy due to the wide application in a domain like astrophysics and the plasma physics, many researchers studied the existence and the controllability of the stochastic magnetohydrodynamic system. And with the aid of Stokes operators, stochastic calculus and semi-group theory, they present the magnetohydrodynamic system in the reformulated in abstract form. Yoon and San recently, just I think 2021, they proved the well-posedness and the dynamics of the stochastic fractional magnetohydrodynamic equation, but without any application. Then after the same guy, Yu and San, they also in 2021, I think so, they proved one result that was based on the ergodicity of the stochastic magnetohydrodynamic system, again without noise term, without application. The non-stationary compressible fluid flow in the model by the Navier Stock equation and its optimal control that was studied by the Hyber, and then after the optimal control of one-dimensional magnetohydrodynamics without stochastic perturbation is studied by Rand. So this is just the recent development in the field of magnetohydrodynamics with respect to the controllability. Applications. There are several applications of magnetohydrodynamic system. The first one is the astrophysics and the space physics. These people, they are just trying to understand the plasma and the magnetic fields, the cosmic environments, nuclear fusion research. They are preparing the model plasma instability in the fusion devices, plasma physics, then space weather prediction, magnetohydrodynamic generator for the power generating using the kinetic energy conversion, geophysical fluid dynamics, that is to understand the Earth's magnetic field and the core dynamics. Mainly, I'm going to talk about this part over here in the turbulence flow control, that manipulating the turbulence flow in the industrial application. So these are various applications of magnetohydrodynamic system. The solar wind is a continuous stream, and the charged particle, primarily electrons and the protons, that emanates from the sun and travel through the solar system. I'm going to work on this one. We are going to discuss about this thing. When the solar wind encounters Earth, it interacts with the Earth's magnetic field. So, solar wind with Earth's magnetic field, that creates a dynamic and complex kind of system. And the stochastic magnetohydrodynamic system is used to model this and simulate the behavior of such kind of system. It considers the random or the turbulent nature of the plasma and the magnetic field involved in the interaction. The stochastic model takes into account the turbulence fluctuations in the solar wind and the Earth magnetosphere. I repeat, the turbulence fluctuation in the solar field and the Earth magnetosphere. These fluctuations can have a significant impact on the dynamics of the interaction. And the stochastic magnetohydrodynamics system, what I have considered over here, that stimulates simulation help to predict the behavior of the solar wind and its impact on the Earth magnetosphere, providing advanced warning for potential space weather events like this. Of course, we are going to learn over here this stochastic. Just skip this one because of the limitation of time. So methodology, we will discuss when the time will come. Let me just give the brief idea about this one. We are going to use over here the topological and the variational method over here. The topological method, why? Because the topological method are obtained from fixed point theorem and are usually based on the idea of the topological degree. And the variational methods represent the solutions as critical points of the stability functionals in the and to find some ways of locating them. So that's the reason we are going to use these type of things. Now we are going to use over here the fractional Brownian motion. So let me just give you the brief idea about the Brownian motion, what we mean by the Brownian motion. Brownian motion, actually the Robert Brown, he was the botanist. He figured it out this thing in 1828, and by his name, this kind of motion that is called the Brownian motion. So Brownian motion actually is an irregular movement of the pollen grain suspended in a water. And the mathematical representation, mathematically we can say it is natural to use the concept for stochastic process dt omega, interpreted as a position of the pollen grain omega at time t. Positions, I'm talking about this one, position of the pollen grain omega at time t. And in finance, the continuous stochastic perturbation will be modeled as a stochastic integral, is so-called Brownian motion, or we can say the Wiener process. The practical application, seeing a drop of ink spread in the water. See, if drop of ink is there in the water, and if the way it's spreaded, that motion itself is the Brownian motion. And but this Brownian motion, they are independent. There are practical systems, multiple practical systems in which this motion that is dependent, and that dependent motion itself is known as the fractional Brownian motion. So let me just give you the definition of Brownian motion. It's a well-known definition, long but that was proved. This is my probability space with the filtration Ft, we can say. A one-dimensional Brownian motion is a real valued continuous function Ft adapted by the process Bt like this, that b 0 equal to 0 almost surely, and bt minus b is normally distributed, the mean 0 and the variance t minus s, and bt minus b is independent of fs. That means whatever the spreading is there, if a drop of ink is there spreading in the water, that process is independent. There are several applications also, the motion of pollen grain in water, the movement of dust particle. We are right now in the room, but there are some dust, and this dust particle, they are also the independent. So diffusion of pollutant in the air, diffusion of calcium through bonds. If you take some calcium tablets and the way that calcium goes to the bond, that is spreaded in the liquid form, so that is also a Brownian motion. The movement of holes of electrical charge in the semiconductors, another applications. So the fractal Brownian motion. That is nothing but the generalization of Brownian motion, and unlike classical Brownian motion, the increments of the fractional Brownian motion need not be independent, as I told you. So definition is given like this: for any age in 0 to 1, a continuous center Gaussian process WHT, T belongs to this interval, we can take an infinite interval, so with the covariance function, this one. Thanks to Tudor, he proved this theorem long back. Now, there is one controversy over here. If this h belongs to 0 to 1, this h is known as the used parameter. If you take h is equal to exactly half, your fractional Brownian motion is converted in terms of a standard Brownian motion, or you can say the Wiener process. That means you have two options. One is open interval 0 to half, and another is open interval half to 1. And people say that you can work with your use parameter lies between the 0 to half and half to 1 open intervals, but I don't agree with that because there are no practical applications. If you take h less than half, it's between 0 to half. In that case, what happened? The increments of the process are negatively correlated, and no applications are there. So that's why I just would like to stay with the h belongs to half to 1 because it is positively correlated. The main difference between the fractional Brownian motion and the regular Brownian motion is that while the increments in the Brownian motion are independent, increments of fractional Brownian motion are not. Already we discussed this thing. Now let me talk about the Poisson process. What we mean by the Poisson process, because I have worked with the Poisson jump. Sorry. A Poisson process is a type of random mathematical object that consists of the point randomly located on the space with the essential feature that points occur independently on one another. So when points occur, points are independent, that is the Poisson jump, and then when points, what your jump depends on the previous one, that is called the random process. The definition, that is well-known definition, the KT is a sequence of independent exponential random variable with a parameter lambda, that is given by this one. This is called the Poisson process with the intensity, you can say, lambda. The random measure, that is, this is the definition, that probability space filtration is Ft. Poisson random measure with intensity measure lambda is a family of random variables, that is set NB, B belongs to F, filtration set, defined on the probability space, this one, such that this B belongs to F, and NB is a random variable with a Poisson distribution. And for any pairwise disjoint set B1, B2, B3, pairwise disjoint, then NB1 and NB2, they are independent. Applications. I told you that I would like to provide you application of each and everything so that you can come to know that why these terminologies are being used for the control problem of stochastic magnetohydrodynamics. The Poisson process or Poisson point process, there are two ways. One is defined on the real line, and that can be considered as a stochastic process. And in this setting, we have the examples in queen theory to model the random events such as the arrival of a customer in the store, phone calls in a phone center, then exchange, or I mean to say that occurrence of the earthquake. These type of problems, they are the Poisson point process in a real line. In the plane, the point process are known as this, sometimes called the spatial Poisson process, can represent the location of the scattered object, such as the transmitters in a wireless network. This kind of random measure is often used when the description jumps of a stochastic process. In particular, there is a Levy noise. Very few people are working in terms of the Levy noise. And there is another kind of thing, that is the Black-Scholes model. Let me just skip this part. Now the stochastic differential equation in the abstract form. Abstract, I mean to say the infinite dimensional form. So dxt is equal to axt, f of txt, g of t. This is my stochastic term. And initial condition is that A is the infinitesimal generator of C0, a strongly continuous semigroup, not necessarily compact, because we are in the infinite dimension space. If you are working with the compact semigroup, that means according to the results of Robert Trigiani from University of Virginia, he proved one result, and in 2007, And he said that if you are working with compactness assumption of the semigroup, that means you are no longer working in the infinite dimension space, but you are falling to finite dimension space. In 2007-8, my first PhD student and we were facing the same problem, and finally we got the breakthrough. And we heard that thesis that was completely based on this one, non-compactness assumptions of the semigroup, and we proved the controllability results. So that is the stochastic process over here without assumptions of the compactness. Let me give you the brief idea about the procedures of the existence of this kind of stochastic differential equation. We define specific norm in the space. We define the mild solution. We define Lipschitz continuous with and as well as non-Lipschitz continuous also to prove the controlled result. Lipschitz continuity, that means definitely you can use the Banach fixed point theorem, you can get the unique existence and uniqueness in a very straightforward way. But if it is non-Lipschitzian, then you have to try, find some way out. Compact operate in the finite dimension, that is good, but infinite dimension, no, not allowed. And then find the suitable fixed point theorem and change the problem solution into the problem in terms of the fixed point theory. Now, the stochastic partial differential equation in the infinite dimension space. So we can consider kind of heat equation over here, stochastic process over here with this condition. And these kind of equations, they are highly useful in physical and chemical models, biological models, engineering models, etc. Existence of a solution, again, we are going to follow same kind of things for the partial differential equation too, with some other assumptions, some changes in the assumptions. Now let me talk a little bit about the optimal control of the stochastic magnetohydrodynamic equation with Poisson jumps. So optimal control in the context of the stochastic hydrodynamic involves the application of the control theory and influence the behavior of the conducting fluid, we say plasma, governed by the stochastic magnetohydrodynamics equation. Now see here what happens if the system jumps from one state to another, the strength of the system becomes random. And in this case, the Brownian motion is insufficient to model its behavior, and that's why we rely on the fractional it's a Poisson jump motion, Poisson point jump. Motivation already I gave you, so let me just skip this part. Because we are taking the combination of Navier Stock equation, Maxwell equation with noise and these terms. So let me just come to the problem. Model description of stochastic magnetohydrodynamic system. Consider the problem like this dV minus nu of delta V. This is a Laplacian V and this one. So this is the problem. Just look at this problem. Here this V is nothing but the velocity, this small v, that is the velocity, and this P cap, this is nothing but the pressure. H is nothing but the magnetic field of the fluid, and combinedly I can combine the whole pressure P cap plus H square by 2 as some capital P or like this. This nu and this gamma, they are this nu and gamma are the viscosity and the magnetic diffusion coefficient. This is the viscosity, velocity coefficient, and this one is the magnetic diffusion coefficient, this gamma. For the sake of simplicity, let me just take nu and gamma is equal to 1 so that my coefficients are 1 so that it is easier for me to calculate for the calculation process. And P, as I told you this, I would like to consider the pressure P. Let the smooth and the bounded domain D in RD with the mixed boundary condition. This velocity is equal to 0 on the boundary, and my velocity as well as the magnetic field. Magnetic field with inner product, I'm going to say dot product of magnetic field with the unit normal that is equal to 0, and the curl of H, curl of the magnetic field, cross product with the unit normal that is equal to 0 on the boundary. So if that happens, now we are in the partial differential equation domain. That means you cannot use just LP space, but we have to specifically use the space, which is a subset of LP space, and I would say it's Sobolev space. So LP represents the closure of collection of all these operators Z, such that Z belongs to this one and divergence of Z is equal to 0 for 1 is less than P is less than or equal to infinity. And with the aid of Helmholtz decomposition, this is the Helmholtz decomposition, where this capital V is nothing but the Laplace, this is the del of Z, where Z belongs to W1P, this is Sobolev space. Sobolev space of with the distributional derivative 1. I would recommend to, if somebody is interested, I would recommend, somebody is working in the field of functional analysis, I would recommend the book of Kesavan. Used to be a professor of TIFR Bangalore. When I was at ISC Bangalore at that time, I got the opportunity to discuss with him, interact with him so many times. And I would just let you know, let me just tell you at this moment, when I went to Professor Lastieka Trigiani in University of Virginia, very famous, renowned professor, in her rec, I saw the book of Kesavan, that is Sobolev space in its application. That's the value of that book. I met him in ICM conference also, so fantastic person and very nice book, very nicely written book, based on the Sobolev space. WMP denotes, as I told you, Sobolev space with the distributional derivative up to order M, P, operator P, that is LP to LP, be the continuous projection, and we define this LP like this one, the LP cross LP. The abstract formulation of my problem, now whatever problem I give it to you, with boundary conditions, the abstract problem formulation that is converted in terms of these two problems, that is a Stock problem, that negative of Laplacian V plus del of P, that is equal to F1, this dot product equal to 0, and velocity of the boundary is equal to 0. This is a Laplacian operator, as I told you, LP, such that the domain of this Laplacian, that is nothing but collection of all velocity operators in the Sobolev space of order distributional derivative 2, with the condition that velocity acting on the boundary that is equal to 0, and we define this A1 is equal to negative of P, Laplace P delta, with the domain of A1 that is equal to LP intersection domain of A. Same way, we can go for the elliptic equation. This kind of Navier Stock equation and the elliptic equation, there is a curl of H that is equal to F2 with these boundary conditions. Again, we can define that A2H is equal to F2 and domain of A2, again that is in Sobolev space, and the sequence AI is nothing but the operator, sequence of operators AI that is isomorphic, and the operator is self-adjoint and compact in L2, and there exists the orthonormal basis EKI in the domain of A of I, which are the eigenfunctions of AI. And this lambda k is the sequence of corresponding eigenvalues such that 0 is less than lambda 1 is less than lambda 2 and so on. The representation of the nonlinear coupled equation, coupled term BC, that is in this form, let me denote by BC, and this is also BC, by applying the continuous projection operator P on my system 3 and 4, that can be now written in the form of dZt equal to this one. Look at over here. So whole problem partial differential equation that is now that boils down to this type of problem. And if you add some control term over here, then your system 7 will be converted to system 8. Just I have added control term over here, the whole problem that is converted in this form. So now I am in this domain of control field. I have defined specific norms over here. Those who are in the field of control theory and the stochastic process, they know it very well, how to define the norm and these things. Let n dt be the Poisson continuous measure, which is induced by the Poisson point process in the measurable space, z and beta z defined the complete probability space, this one. And the compensator martingale measure, that is this one. In my system, you can find this type of terminologies that is actually nothing but the martingale measure. So, A is the boundary linear operator
sir,
which generates the semi-group. U is a control term, and this control term, that is estimation of integral of this one, that is finite, and endowed with this norm.
Sir, just a minute.
Yes.
Sir, there is a time limit for us, so can we go
Yeah,
through,
I
can
know.
we conclude, sir?
It's been 20 minutes, right? I have half an hour.
Okay, sir. Continue, sir.
So I have 10 minutes. If you allow me, otherwise I can stop.
No, sir, continue. No problem.
Okay, thank you. The analytic semigroup generated by A, that is this semigroup ST, that is bounded by this one, and these are the, that's what actually proved in this reference. This estimation that was put over here. Let me just go very quickly. So the mild solution of my system that is given in this form, once you have the mild solution, then naturally we can go for some hypothesis and try to prove the existence and uniqueness of the given problem. This operator either satisfies the Lipschitz continuity and boundedness, and this is I just assign the operator so that I can work with the boundedness of the operator. These are the terms: phi maps bounded set into the bounded set, phi zt is a continuous on DL, and phi is a contraction mapping. Once you prove these three things, if you want, you can refer my paper, then you can find the existence and uniqueness of the solution. Optimal control. This is the cost functional Lagrangian optimal control problem, and we find the optimal pair like this: U0, Z0 and U0 in this one. For any U belongs to this one, and then we have another set of assumptions to prove the optimal controllability of the system. So if all the assumptions in the theorem that is satisfied with hypothesis A2, this operator A is strongly continuous operator, then the Lagrangian operator control problem has at least one optimal pair. I have proved this one also. Let me skip the proof. And now let's talk about the trajectory controllability, and I will just try to conclude in next 5 to 7 minutes. Trajectory controllability, as I told you, that once you have the solar wind and earth magnetic field, if they are interacting each other, if you know the path along which your system moves, there are possibilities of figuring it out so many things. Recently, India just launched the Aditya space shuttle, and I think this type of NASA or ISRO, this type of organizations, they can use the problems which we are studied over here. They are very much correlated. I worked with NASA for almost 1 year, before seven years, and it was a very fantastic experience, and they are highly related with the control theory. This paper actually published recently, just I would say this month. It was accepted last month. It is published this month. That is in Chaos Skeleton Fractals Elsevier Q1 journal, and impact factor is 8.5. Acceptance rate is just, I think, 16 or 17%. Motivation, already we discussed these things, so let me skip this one. And novelty also we discussed, so let me skip this part also. This is my problem to learn for the trajectory controllability. This one. It's impossible to cover everything just within half an hour, because it's almost 1 hour talk. And just yesterday I came to know that I have to talk only for half an hour. So this is the boundary condition, whatever we discussed, and then after I have proved the trajectory controllability of the system with this control. So this is the controllability, and the total, the trajectory controllability, we induce the control problem 13 in this form, and then after we go for the definition of trajectory controllability, because control definition that varies system to system. So first of all, we have to define the set. So the script top be the collection of all functions pi defined on 0 to t with pi 0 equal to xi 0 and pi equal to pt, where pt is a reachable set at time t. Here tau stands for the set of all possible trajectories for the control model 3. So using this set, we can say that control system 3 is trajectory controllable if for given initial condition there exists the control W in this space such that the mild solution of this one satisfies xi rho equal to pi rho almost everywhere. That means now we are measuring our system on each and every point along the path. So I have this is a theoretical portion. Let me just skip this part also. And this is the mild solution of the system. Once you have the mild solution of the system, then after we can go for some assumptions. I have assumed we have some hypotheses over here. And finally, using this hypothesis H1 to H2, there exists a unique mild solution of the control problem, whatever I just showed you, 14, with the constant C1 less than 1 and the C cap less than 1, C cap that is given in this form, where C1, C2, C3 are defined in this format. If the assumption H1 to H3 are satisfied, then stochastic impulsive magnetohydrodynamics model 3 is trajectory controllable on this interval provided t minus t is greater than 0 and with respect to this condition. So Let me again just exclude the proof. This is just the system and the mild solution, and we can just go over. Let me just take the example. This is the practical example, numerical example that helped me a lot to figure it out the numerical simulation. Because of limitation of time, it's not possible for me to go through the numerical simulation, but I just proved the numerical simulation that matches exactly with my theory. So that is the advantage of this work, because nowadays just theoretical work, where always it is, I have found this thing, those who are good at theory, they have some lacking part in the numerical side, and the vice versa also. But if you combine both things, because I think mathematics applied and pure, they are just two sides of one coin. And you can see here the magnetic field evaluation with the spatial location. So this is nothing but the magnetic field, and same way, and this is three-dimensional magnetic field. If you know this, if you can control this one, that means you can have some fantastic result and some good things can come out. And this is my velocity field evaluation. This is the velocity field evaluation, again in 3 dimensions, the visualization of the magnetic field as well as the velocity field. And I have used this conclusion. You can convert this one if you have some proper applications. You can convert this one in terms of the fractional order system also. But make sure that when you use the fractional order system, just stay with either Capurro derivative or Hilbert fractional derivative, or you can go for the Hadamard derivative. Right now, you can find so many new derivatives like Tata-Gumpo derivative, AB, Atanuta-Baleno derivative. They just made some changes in the operator and create new derivative without any application. I bet you, if you find any of the application for these newly developed fractional order derivatives, I did not get it so far. If you get it, please let me know. But so far, in my knowledge, there is no any kind of application. Don't use this type of derivatives. Just stay with only these 3 derivatives if somebody is interested. I have used these references to prepare this talk. And thank you so much for the invite. And I would like to request, of course, this is not the full talk, but even if I would like to request the organizers to send me this link so that I can upload that link in my YouTube channel. So if somebody is interested from the audience, they can look at the channel and they can just, it's open for everyone. So may be useful to the participants. Thank you so much, and thanks for the invite.
Thank you so much, sir, for the great talk. I would like to request Dr. V.D. Pathak, sir, chairperson, to comment on the session.
I must say that I've seen Dimple Chalisadar as a student, research student in our department, and the progress that he has made. I'm very happy about that. He has touched the strong theoretical part and very wide applications actually. So both the parts, the theory and the applications, he has touched in his talk. He talked about many concepts actually, trajectory concept. Let me just say that some keywords from his talk, if you look at, you can say trajectory controllability, then stochastic magnetohydrodynamic equations he's talking about. Now these equations are dependent on 2 types of equations, the Navier Stock equation and Maxwell's equation. Now both is independently. If you want to handle these equations, that is very, very difficult. When you are combining it, the complexity will definitely increase. Then you are talking about Brownian motion. So we are adding a kind of uncertainty. Where from this uncertainty comes from? Because they are using, for example, they are using in the turbulence fluctuations of the turbulent fluctuations of the sun and magnetohydrodynamic field of Earth. When they are talking about interaction between this, the uncertainty comes from the turbulence, and the other magnetohydrodynamics things will come from the other hydrodynamic field. So these things are coming. So whenever we are trying to listen to such lectures, what is important is that we cannot understand the complete theory. It is impossible because it is quite involved, deep theory. But we can look at the keywords and correlate with the areas where the applications are going to be are being done. You can see that he is talking about Wiener process. Now Wiener process comes in financial mathematics. You are talking about Black-Scholes equation. Black-Scholes equation govern the behavior of the stock price variations. So you can see that the range of the applications that are based on this kind of theory is quite wide. And so, and at the midnight, when everybody is fast asleep, he is giving such an enthusiastic lecture. I really appreciate that. And I think we don't have time to question answers, right? No time for question answers. Otherwise, I would have allowed you to ask me questions. But if you want to ask him questions, you can write to email and all that you can do.
Yeah, you can send the email to me and I will try my best to get back to you as soon as possible.
Sure. So I congratulate Dimple for a wonderful lecture, which is covering wide range of applications and strong theoretical basis. Theoretical base gives confidence to the application-oriented mathematicians. And therefore, I congratulate and let us thank Professor Dimple Chalisizar for a wonderful talk, which is right kind of talk for such an conference. Okay. Thank you very much.
Thank you, sir. Thank you.
Thank you, Pathak sir. Thank you, Dimple Kumar sir. I would request Dr. Arshad Patel sir to present certificate to our chairperson, Professor Dr. V.D. Pathak sir. I would like to thank Dimple Kumar Chalisizar sir for sparing their valuable time with us. As a token of appreciation, we would like to present e-certificate to sir.
Thank you so much.
Thank you so much, sir.